So the next speaker will be Farbod Hassani.
Yeah, thank you. Thanks to the organizers for organizing such a nice meeting, especially me. So I'm gonna make this talk very introductory. I hope you can take away something. So I'm gonna talk about probing dark energy models across scales. This is something that I've been working on for several years. That's why you see lots of collaborators, and also especially within nuclear collaboration. All right, everything started with this interesting finding of supernovae observations that two independent research teams found out that we have late accelerating expansion of the universe, and you all have heard about. And for several years, there were people in theory that were speculating different dark energy models or modified gravity models, which could give rise to this late accelerating expansion. And after several years of silence from a survey team, there was this interesting report of the Dark Energy Task Force, which was advised to several funding agencies in the US, like National Science Foundation, and it was supposed to be on future dark energy research. And it's interesting, the first point, to see how desperate they were at the time. We strongly recommend that there be an aggressive program to explore dark energy as fully as possible, since it challenges our understanding of fundamental physics law and the nature of the cosmos. And I think we are still there, so at least I am. So we haven't found much about dark energy. And there was this Euclid mission as well, which was supposed to increase our precision in equational state, as well as the growth factor to help us to probe dark energy better. All right, if you think about this in a theoretical way, you might find it very counterintuitive, because from Poisson's equation, if you put any type of matter, you have gravitational waves and basically make things attract, right, to this, fall into this gravitational waves. But it's not hard to realize that you add a constant to this equation, basically, you can make things recede from each other at large scales. Basically, it makes a global trough in the universe, which these galaxies are receding from each other, but they have their own potential. In the covariant form, it looks like this. This is the Einstein's equations with the open material constant. You can stop here and say, okay, I'm happy with cosmological constants and new constant in nature. Okay, I don't want to continue, but I would like to continue. So people have thought, okay, maybe it's not a constant, it's a scalar field, it's a new type of matter, which might be relatively homogeneous through space and might not change much in time. But let's at least speculate this possibility. And they have called this dark energy. But if you put it on the left-hand side and different possibilities, people have called it also modified gravity. They are not really distinguished very necessarily. So the question is, how can we add a scalar field as a possibility of dark energy phenomenon? And that's, here it comes, the Hornetsky Lagrangian is the simplest viable class of alternatives to Lagrangian. And if we assume that the speed of light, the gravitational wave propagation is the same as the speed of light, then we end up with these terms in the Lagrangian. So this is the fully general way that you can think of a scalar field and can give you the dark energy phenomenon. They have their own names because people in the past were considering these theories independently, like KSN's was developed in 1995, if I'm not mistaken, or 2000. I don't remember correctly, but the KGB, minimum non-minimal coupling. So these are all possibilities. And but what you have to do, or what people have been doing, they were considering certain theories like quintessence, which you are familiar with, KSNs, and etc. They solve the equations, the scalar field evolution, and what at the end of the day they need to do to compare with data, they have to assume a model, right? They have to think of a model for the potential, how the potential evolves. There is a free parameter, and then they want to constrain those parameters with data. And as you can see, there are infinite amount of parameterizations in this type of theories, right? And it seems that we are doomed, but there is a way, and that's the effective theory approach. Luckily, there are some assumptions that you can make, which is relevant for cosmology, like the fact that the gravitational potentials are small, the static perturbations, if you assume to be small, then you can realize immediately that rather than focusing on these functions and finding a parameterization for these, in fact, they just become some time-dependent free parameters that can be constrained with observations. It's very similar to what we do usually. We have been doing like in high school physics. Imagine somebody tells you what's the you have the initial position and velocities of all molecules in this room. What's going to be the next configuration in 1 second later? What would you do? You are not going to run a simulation program, like a computational program, to solve all these complex interactions and to find what's going to be the final state, but rather be actually effectively describe this system using some effective parameters like pressure, volume, temperature, and electron. It's exactly the same. So rather than thinking of all these details in these theories, we actually, or for cosmological studies, we only need to know these parameters. Okay, I think I'm going to be faster. In the past years, because of the CMB, and CMB was linear perturbation theory was enough. So people have implemented these 3 parameters in the Boltzmann codes, high class, EFT-CAM, and etc., and have been studying how CMB can constrain these parameters. And there were some constraints, but now we are entering precision era of cosmology. We are going to have nonlinearities, and our point is that linear implementation is not enough. And these models actually have some phenomenology which is missed completely in linear studies. So here it comes why we need to run or implement these theories in n-body simulations. We can focus on observables in simulations and higher order statistics which are absent in linear study. We can discover new probes through accurate study, and also most importantly, we can actually constrain these theories even without requiring data, because what happens is that some of these theories show some nonlinear instabilities, and you can rule them out without even going to compare data. It's very important and interesting. All right, so to do that, we use G-evolution. It's a relativistic n-body code. We solve the full Einstein's equations, 6 degrees of freedom of metric in percentage, and we evolve the particles using the geodesic equation. And the reason we use the relativistic code because it's more natural for dark energy theories, which can be relativistic. This is a picture. Actually, I made it a week ago. I wanted to apply for a grant, so apparently putting it into grants proposals help. So these dots are halos in an n-body simulation. These streams are the vector perturbations or frame dragging effects in a relativistic framework. It's just it's non-scientific, but it's cool. All right, so what we have been doing so far during past years, we have finished implementing K-essence type theories and kinetic gravity braiding, which we have boxed by. And we called it different code because it took us 3 years each. We had to really call it something. And eventually what we are going to have is the full Hornetsky implementation in n-body code. And we are going to use in Euclid collaboration to constrain these parameters in a consistent way. All right. So what we are going to have in this code is that dark energy is an independent quantity, as expected in these theories. So it can independently evolve based on the equations that govern their evolution. So we have here is on the right we have matter density, and on the left we have dark energy density at redshift 6. And when we go ahead in time, we see that there will be nonlinear structures of dark energy now around matter structures. So what we have done, like to constrain these theories so far, we have been making pipelines through n-body simulations, snapshots, and light cone generations to see what are the signatures of these dark energy models. So these are tasks we have been doing. We have studied dark matter, halo power spectra, monopole, quadrupole. These are the couple, and these are like going to be in a pipeline, which later on people just can run and extract this information using the snapshots, the simulation and light codes. Higher order statistics, ISW, weak lensing, gravitational lensing, and number count spectrum in the past light component of observer. And we have also gravitational waves background because it's a relative. So these 2 degrees of freedom of gravitational waves are present, sleep parameter, and so on. And at the end of the day, for Euclid, I think what matters is we have to develop emulators. So because we cannot run simulations easily. Thank you. Just one slide before going to conclusion is that actually there was a talk by Farbod Hassani 2 days ago about the reverse ISW effect in the nearby universe. And in 2020, actually, we had this figure. If you have K-sense type theory or dark energy fluid with the same equation, I would say, with the same background, expansion history, only changing the CS squared, whether dark energy can cluster effectively or doesn't cluster, you actually see that the ISW effect would be completely different. So this orange is the colorblind friendly. So I don't think they have names, but this corresponds to 10 to the minus 7 case, like the speed of sound squared, and this curve corresponds to when we have CS squared equal to 1, where we don't have clustering of dark energy. And this might help to actually explain what Farbod Hassani was. We are going to expect this. Okay, I'm going to leave you with the summary. Just one take-home message would be, we are going to implement all these Hornetsky parameters, and hopefully we are going to use them within Euclid collaboration to put some constraints on this. Thanks. I needed focus.
Do you have an expected timeline on the implementation?
So 2 of them are already implemented, which took 6 years. It's hard because you have to do a lot of tests, and there are lots of issues in MLE. It's not like class or high class implementation. We have people from high class, which help us in Boltzmann part, but this is a hard problem.
Is it getting easier?
I think so. We hope so every time, but so there was a new Martin. It was the idea of my PhD supervisor, Martin Kunz. Actually, I was doing this in my PhD during my PhD for the idea of full Hornetsky implementation. We ended up with 1, and then he got a new PhD student. He ended up with 1. Maybe the next PhD.
Now you also have that, so it will take longer.
Okay.
Can't remember one.
Why we consider that is the full way of considering a scalar field as a dark energy to explain dark energy phenomena. So it includes all the possibilities that you can have on a scalar field.
That was observational argument.
And it was ruled out.
So one of the parameters was ruled out, which actually I didn't include. That was because of gravitational wave propagation was equal to speed of sound. That ruled out one of the terms completely, which we didn't consider at all. Yeah, but we didn't have it here.
Any other question? Okay, so let's thank the speaker again.